Hey there, guys and gals. We're going to be talking about rate of change and slope, as our title says. This particular topic is not a new topic for you, or it shouldn't be. You should have seen this in Algebra 1 and probably even sooner than that. The biggest thing that we're kind of doing here and we're continuing to do is we're pushing more and more abstract. We're kind of climbing higher and higher in that tower of math, because this particular topic is a topic that's going to come up over and over again, and we're going to get more and more abstracted in there, and we're going to apply it to more and more different things. And because, we're going to talk about rate of change, we're going to talk about slope. These are things, when you learned how to graph a line, back in Algebra 1 or even pre-algebra, when you learned how to graph something like that, you know that slope is rise over run, and you know that it's the difference of the y's of the different. You probably know all of that. You probably know most all of that, or do. And especially if you've been in one of my classes before, you know that pretty well, and you may have even seen some of the formulas written in the way that I'm going to write them here, because I've found that the higher the level that we teach at each individual level, the less issues we have as we transition and we continue to grow and do things. So rate of change is a really important topic. It's an important excuse me. It's an important topic in math. It's an important topic in science. You see this in chemistry. You see this in physics, even in biology, actually. So rate of change is a bigger concept. Now, slope in particular, the difference between concept of rate of change and the word slope and the concept of slope is really the only time we use the word slope is when we're talking about linear functions specifically, right? Other than that, we talk about rate of change. Now, these two words are essentially interchangeable. Rate of change is the same thing as slope, basically. We just don't usually use the word slope unless we're talking specifically about a linear function, right? And so that slope being that m part of the y equals mx plus b and all of that stuff. So rate of change, simply put, now this is Algebra 2, this isn't pre-cal and it's not calculus, right? Rate of change simply put, and this is true in all of the times in math and science when this is used, is rate of change is how fast something is changing. Wow, that sounds like rocket science. It really isn't, right? How fast something is changing. So in the context of, say, a physics class, right, you might have the rate of change in position, right? So just as a brief aside, we might have the rate of change in position, which is defined as velocity. That little symbol there is vector. We're not going to get deep into all of that. We are going to talk about vectors later this year, I think, if I'm not greatly mistaken in my memory of what's in this class. We are going to get into vectors more specifically later. And you may have, depending on your geometry education, you may have seen some stuff on vectors in there. May have not. I don't know. Your mileage may vary, but rate of change is always the change in something, and it's almost always over time when we're talking about real stuff. So like velocity is the change in, I'm going to get more specific on this in a minute. It's the change in position over time, right? So you might over the change in time. So something like that might be like a physics example, but this is not a physics class. I know that's a shocker to you that this is not a physics class. It's not a chemistry class. And so the difference between like something you might see like this in a physics class is in a math class, we like to go even more generic. We like to have a formula that applies to a whole lot of different contexts. So rate of change in its most generic form is the change in y. Now, well, let me get this whole thing written out, and then I'll say now. Okay, so the change in y over the change in x. Change in x. Now, what does that mean in a generic? So so that's really, really generic, and that is what rate of change is in the math context. That's how it's defined. Now, there's an easier way to write this, you may know, because this phrase change in has a shortcut. You've already seen it over there to the left if you've never seen it before, because we can write change in with a nice little Greek letter here. This is a Greek letter delta. So delta means change in. That's what that means in math and science, for that matter. Okay, so if we want to rewrite this in a shortcut form for our rate of change formula, it's the change in y over the change in x. So same thing, but with symbols. Beautiful. We like symbols in math and science as well, but we like those because it makes it easier for us to write. Right? Math teachers and math people are just lazy grammar nerds, right? We're just following the rules. So why do I hate grammar so much? I don't know. Anyway, so that's what this is in its most generic term. Now, it's worth note, and we're thinking about, say, so x and y, what are they? They're generic variables in math, right? But they mean something, right? So the x and the y, they're not just kind of generic things, right? So what are they? Even more specific than that. They are, let's use maybe a white. So the y, what is y? We know this from all kinds of other things. The y is the dependent quantity in a function. Dependent, right? And the x is the independent quantity. So it's the change in the dependent quantity divided by the change in the independent quantity. And that is the most specificity we get for now. Dependent. Okay. Right? So that's what we're talking for the most generic high level that we're getting so far for rate of change is its change in a dependent quantity divided by the change in independent quantity. When we get to things like physics and chemistry, the independent quantity is almost always time. Almost always, right? That's you're going to see that in your physics class and your chemistry class. You're going to see that over and over and over again in varying ways. Now, in math, we can get a little bit more specific. When we're talking about slope in particular. Slope, again, we're talking usually about a linear function. Right? So slope, we can calculate. Now, it's the same thing here. So this is equivalent to this other formula that we're going to write, right? When we have change in, and this is true in physics, this is true in chemistry, this is true in math, it's almost always the final quantity minus the initial quantity. Now, in math, we generify it. I don't know. Is that a word? I don't know. Let me know in the comments or in class. Is generifying a word? I don't know. We're going to make it even more generic, than the final. We're going to just say the second one, right, as the final. So the slope formula, which you probably have seen before, is y2, the second y, minus the first y. Now, in a physics or chemistry context, this would be like the final minus the initial, right? But in math, we go to a more generic rule that applies to more context. So we just say the second one, right? Minus the first one. Oops, I did x again. I did y again. How about x2 minus y2? And the reason for all these extra words, when you watch this, there's a rate of change in slope video in my Algebra 1 course and in other people's Algebra 1 course. In those courses, I don't spend as much time saying as many of these words as I do there. I just kind of say, this is a thing. And then we end up with this formula in the end. But the higher we get in math, the more we're kind of seeing how it overlaps and how it applies to these other spaces. And so that's why we're spending this extra time kind of thinking through all of these things. Now, the one more thing that I want to say here let me make sure. Yeah. Okay. Oh, look, I have I'll pick that up again here in a second. The one more thing that I want to say, and this is kind of something in passing in the textbook we're using in my classes, it's got some more specificity here, but I want to just kind of put this little bug in your ear. I don't know, gross visual. I don't know. I'll come up with a better something for the future. So if I wanted to take this, and this is something kind of pushing towards pre-cal and pushing towards calculus, if I wanted to take this green thing here and I wanted to say, okay, what's the slope of that? Well, I can't do that, right? But I can sort of figure out, okay, the slope right here is the same as this slope, right? And then right here, it's the same as that slope. And so the slope changes. And if you're doing a function where the slope changes, something like this, I'm kind of doing a relatively poor job of sketching it, but the slope changes. And so that's something that we're going to see in calculus as we see the slope change and how does it change and all of those things. So we're going to see that rate of change, the slope change. And that's something that we're going to push to in the future. So we're not talking about a linear function. We're talking about something else. You can see scenarios where your slope or your rate of change changes over time, and the rate of change is where we get higher and higher concepts. Actually, if you've taken physics or are taking physics, you probably have actually seen that, because like I just said, velocity is how fast position is changing. Well, acceleration is how fast that velocity is changing, right? So we've got the rate of change of a rate of change of a rate of change, and we're going to end up with graphs like this. And so kind of planting these seeds, it's better. That's a better visual than whatever nonsense I said a couple minutes ago. Oh, but as we get higher and higher in this and learn more and more things, we're kind of planting seeds for the future of these other concepts. So the slope formula, we already have that, but just to give it to us in a more official way and a more official context, we're going to do a couple examples here in a minute. M is the variable we use for slope, right? For whatever reason, honestly, I couldn't tell you. I'd have to look it up. Google it. Put it down in the comments. No, you will not get extra credit in my class. Okay, so the slope formula is officially M equals y2 minus y1 all over x2 minus x1. That is the slope formula. And of course, these two things here, this is the slope between 2 points, the points x1, y1, and x2, y2. So let's do a couple examples. One that's explicit given and the other one where we're going to get it from a picture. So let's jump in and let's use this formula. Okay. There's actually, well, we'll do these equations out of order. I forgot that I had two. Anyway, it's fine. Let's do this one first and then the other one next. Okay, so we want to find the slope of this graph. So when you're given a graph, there's kind of two ways to look about it and think about it. So the first thing, and this is true when you're thinking about it either way, and that is you want to find out where your graph, so this blue guy right here, where does it cross at a cross? That's how I describe it, and then I'll show you what that means. So where we want to find where it crosses at a cross. Okay, so what we're talking about by a cross is we're talking about these grid lines. So like this, I don't think that light green is going to show up on there well enough. Let's go for the dark one. That's still a little iffy. How about this purple? Beautiful. Okay, great. So like this would be a cross, a grid cross. This is not where the function is, right? There's another one over here. So everywhere where there's an intersection of our grid are crosses. So what we're trying to find is where this blue, this function that's drawn on this page, where does it cross at a cross? So like, for example, there's a cross right here where it crosses at a cross. There's another one right there where it crosses at a cross. You see what I'm saying? Where it kind of crosses at the grid place, right? So kind of going up here, we've got another spot right here is a place where it crosses at a cross. So then you kind of have two options. Once you've found them, you can do one of two things. You can either use the slope formula, which is, of course, m equals y2 minus y1 all over x2 minus x1. And you can plug these points in. So let's label what these points are. So this one right here, it doesn't go anywhere on the x, right? It doesn't go left or right any, so it's 0 something. Let's count 1, 2, 3, 4, but that's down, so it's -4, right? I hope this is review for you. If it's not, and you're not one of my students, I'd highly recommend checking out some of our Algebra 1 videos. And if it's not a review and you are one of my students, you should probably schedule some office hours because clearly we've got some major gaps. But let's continue on. So let's figure out this point. So we've got -1, 2, 3, 4, -4, and -1, right? So those points. And we've got this final one, which is -1, 2, 3. I just realized this goes to 10, so how about 9, 8? So -8. And up 2, so +2. Okay, so those are the points and the places where the graph crosses at a cross, right? Easy peasy. So we could use our slope formula and just plug in pick 2 of those points and plug them in. So if we did that and we picked this as the first point and this as the second point, let's plug them in there. Let's plug it into the thing and see, and then I'll show you another way you can think about this particular problem as well. After that, we'll do one more example, and then we shall be done. Okay, so we're going to put parentheses everywhere there's a variable, just like we always do when we do substitution property. And the main reason for that, again, for the 50 bazillionth time at this point, is so that we keep our signs in the right place. So I really recommend using this, and so that's what we're going to do here. So we're going to plug in y2. So that would be the y from this one. Points go x, y, always, right? So we're going to plug in -4. And then y1, that would be the y from the first point. So that's -1, right? -1. Then we're going to go down here and plug in x2, right? So that would be the x from the second point. So we're going to plug in a 0. And then we're going to plug in x1, which would going to be the x from the first point. So it's -4. Now we're just going to simplify this on down. We've got minus on both of these places. So we're going to ka-chink those. Yes, ka-chink, ka-blap, blap. So it turns into plus. So on the top, we have signs are different. So we subtract and keep the sign of the bigger one. So that is -3. And on the bottom, the signs are the same-ish because 0 doesn't have a sign. So 0 plus 4 is just 4, right? That's easy peasy. So the slope of this is -3/4. So that's one way you can think of this. You can just pick 2 points, plug them into our slope formula, and move on with your life. Now, another way to think about it when you have a graph is to still figure out where does it cross at a cross. So you're still going to start with that. You're still going to start there. And then what we can do instead of using the formula is we can just do a little bit of looking and counting. So you still pick one. Now I'm going to do this a little bit different. I'm going to pick this one and I'm going to pick that one, right? So then you're going, and when we do this, we always start with the leftmost. So we're always going to count this left to right. Okay, because that's going to tell us our signs. When we start here, and it's always rise over run, right? So it's up and down first, over left and right. So we're got to figure out what to do first. So I'm gonna look here, and I'm going to figure out what do I need to do to get from this guy to that guy. Oh, what happened? Good enough. Okay, from this guy to that guy. So from here, do I have to go up? Or do I have to go down? Well, to get from here to there, I have to go down, right? Which means I'm going negative, right? See what we're doing there? So I'm going to count down 1, 2, 3, 4, 5, 6. So -6. And then over 1, 2, 3, 4, 5, 6, 7, 8. So -6 over 8. So the slope is -6 over 8. Now you might be thinking, you probably are already seeing the future here. You might be thinking, well, that's not the same thing. But of course, take a half a second and look at it. If we reduce -6 over 8, then we end up with -3/4 as our slope. So see, if you get something that needs to be reduced, either method, make sure you reduce that fraction at the end. Easy peasy. Make sense? No big deal. Let's do one more example, and then we will be out. Okay. I guess I forgot to write this example down in my video prep, so we're going to write it together. We are going to find the slope of the line that passes through the points 5, -1, and -2, -3. So this is easy peasy, right? We're just going to use the slope formula. What was the slope formula? It was m equals y2 minus y1 all over x2 minus x1. Blapo. Right? So this is just a simple substitution problem. Now, you may, and this is, if this was Algebra 1, I would be saying, instead of you may, I would be saying you should. But in this class, I'm going to say you may want to label these first, because it's going to help. The more, the more we can kind of take future thought out, the better we can plan our math problems or physics problems or whatever. The better we can plan them out, the less likely we are to make careless mistakes later. Because if we kind of do our thinking up front and then just kind of mechanic our way down and get the answer or that we're looking for, it's just a decent strategy to kind of take the later thinking out. So do the thinking first and then the mechanics later. So let's label this as x1, y1, right? So this is our first point. And this one as x2, y2. Now, you might be asking yourself, depending on how tight those cobwebs are bound up in your head from Algebra 1, you might be asking yourself, well, how do you know which one's the first point and which one's the second point? The short answer is it doesn't matter. But I just always, he's just for the sake of, again, taking out later thinking, I always label whatever the first point that was written is as point 1 and whatever the second point that's written as point 2. So again, it's just trying to take some thought out of it. So we're going to write this with variables everywhere there are, not variables, with parentheses everywhere there are variables. That's what I was trying to say, right? That minus that, and then whoosh, minus whoosh. Great. So the first thing we're going to plug in is y2. We don't have to think because it's written right there for us. y2 is this one. So we're going to put a -3. And then what are we going to put next? Well, we're going to put y1, so we don't have to think. Just put what we already labeled. Easy peasy. x2 comes next, so that's this one. So -2. x1, see, I almost said it wrong, but then I just have to look to what I've already written. So even if you have ADHD brain like I do, and you accidentally start thinking about other things in the middle of what you're doing, like you stop in the middle of a thing and you tell your students about some words, you can still come back and just match. You don't even have to think about where you were because it's just there. So even if you have brain issues like I do, if you do some of these things, it'll help. So x1 is what we're trying to plug in, which of course is 5. Now we've got a minus, so we are going to ka-chink those. So up at the top, we have signs that are different. One's negative, one's positive. And so we subtract to keep the sign of the bigger one. So we, of course, end up with -2. And then on the bottom, we have signs that are the same. So we add and keep the sign. So it's -7. Now we have a negative over a negative, so that turns into a positive. Does 2 over 7 reduce? No, it does not, which means the slope of our line is 2/7. That's it for this lesson. We'll see you in class if you're one of my students. If you're not one of my students, thanks for joining us. Let us know how we can help you with math or science or homeschooling in general. Thank you. Have a wonderful day. Bye-bye.